All right, welcome back. I hope you guys had a great spring break. No, we're not having a quiz because I don't think that would be very fair to have a quiz right after you come back from break. Because who's been thinking about chemistry over break? Yeah, none of us. Jessica? So today we're going to be talking about acids and bases. And so we all heard the terms acid and base. And you notice we have a couple sections here, a section on acid rain and stuff. We might get to that. That's an important consideration that we have in our society today. So we have to start by defining what an acid is. So here is a simple definition of an acid. It's not the only definition of an acid. In fact, on the next slide, I'll give you the person's name. Actually, I think it's two people's names who are associated with this definition of an acid. But an acid is something that donates protons. Actually, it won't be on the next slide. It'll be on the one after that. So an acid donates protons, whereas a base accepts protons. And we have in this picture some examples of acids and bases. So citrus fruits. Most everyone knows citrus fruits are acidic. And you have a lot of household cleaners that are based on citrus fruits. Something that's lime or orange or something. Pickles. A lot of people don't think of pickles as being acidic, but they are. Toilet bowl cleaner. And right next to toilet bowl cleaner, we have Coca-Cola. How many people have heard that you can use Coca-Cola to clean your toilet? You think it works?
Yeah.
Yes, it does. Why would it work? Because it's a strong acid, just like the toilet bowl cleaner basically is. Does that mean that Coca-Cola is inherently bad because it's acidic?
Yes.
Okay, we have a strong yes on that. So pineapple is also very strongly acidic.
It makes my tongue swell.
It does. That's why I use it as my example. I have a reaction from how acidic the pineapple is. So does that mean we shouldn't eat pineapple? No. And I mean, tomatoes, there's a lot of things that are acidic. Just because it's acidic and even reasonably strongly acidic doesn't mean in and of itself it's not palatable. But there are some difficulties. That's why you have things like antacids that some people have to eat. Because your stomach acid is actually very acidic and you need something to counter that sometimes. Bases, on the other hand, an example of a base, baking soda. Anything that's a soda is going to be, except for a soda pop, is going to be basic. And then we have soaps and cleansers are other examples here. So those are just some examples of acids and bases that you regularly interact with. Right? It's not like they're only something from chemistry class. So here is the Bronsted-Lowry definition for acids and bases. And of course, I just had this on the previous slide, although I don't think I spent too much time on it. Acids donate protons, bases accept. And so we have this mnemonic that's bad. Right? It's not hard to remember this mnemonic. Bases accept and acids donate. What is being accepted or donated in either case? Protons. Right, so you have to remember that. It's not a very useful mnemonic if you don't remember that what is being accepted or donated is protons. So let's see a practical example of what this means. Right, having the words really doesn't help me to understand it. So let's look at actual examples. First of all, what does it mean to be a proton? Well, a proton has a charge of +1, right? It's a basic fundamental unit for us. A hydrogen atom is a proton with an electron orbiting it. So if we take a hydrogen atom and we strip it of its electron, then that hydrogen ion is a proton. So with that definition of accepting or donating a proton, that means it's accepting or donating a hydrogen atom in most practical cases. Not in all cases, but in most practical cases. So this is superfluous from what I just said. So in an acid, remember, acids donate So the acid donates a hydrogen ion, H+. The word acid actually means sour. It comes from the Latin word acidus for sour. And so things that are acidic tend to have a sour taste. Hence, your citrus has that sour taste. Bases, on the other hand, are often called alkaline. So, somebody says, this is alkaline soil. It means the soil is basic. And bases are things that are going to accept a hydrogen ion, and they have a bitter taste instead of a sour taste. So we have a certain sensor for acids and bases just in our tongues. So here is the actual application. Here we have two chemicals that are mixed, HCl and H2O. What is the scientific naming that you would use for HCl? Using the naming scheme that we have learned. Yes, you'd say hydrogen, and then instead of chlorine, you change the ending from "ene" to "ide." So that's hydrogen chloride. H2O. Okay, H2O is water. What would its name be with this naming convention? Di, because there's two of them. Hydrogen. Mono, because there's one of them. You don't double the O, aka water. So we're starting with hydrogen chloride and water. Now in this, you can see the reaction is shown. The HCl, what's going to happen to the HCl?
The H is going to be dropped.
Okay, the H is going to be dropped off. What about the electron?
It's going to remain.
It's going to remain with chlorine. So it's just a proton that leaves. So that HCl is donating a proton. What do we call it if it donated a proton? An acid. So the HCl here is the acid. Come on, change. There we go. Is the acid because it donated a proton. What happens to the H2O? It accepted a proton, accepted a hydrogen ion. And so that means that the water here was the base. So we had an acid and a base mixed together, and then we had that reaction with the hydrogen donated and the oxygen or the hydrogen accepted by the other. This is, by the way, called, I was just going to write acid, hydrochloric acid. When you put HCl in your water, the more water you have, the more dilute it is. And so the HCl is the hydrochloric acid. Let's just go to the next slide. Here's another example. H2O. What would we call H2O again? Dihydrogen monoxide. And of course, we all know that's water. NH3. What would its name by the conventions we've used be? Question, Jessica? Or
Yeah, it's a question. I'm so sorry. I don't do that.
no.
But on the test, are you gonna put like little things like this, and we have to like tell you what it is?
Yes.
Okay. Thank you.
So what would the NH and in your homework too? That's the common name. But what I wanted was to work through the naming convention before I was going to say, or the common name ammonium. So what we learned, the general rule was you take the one that's farther on the left-hand side of the periodic table first. And so we would have said, oh, we should probably put the hydrogen first because it's farther to the left. But that's a general rule. It's written here in the order that we would say it. And so we would say first nitrogen. We wouldn't say tri because there's three. Hydrogen, nitride. we would say nitrogen trihydride. Trihydride. But nobody ever does. They say ammonium. And okay, I said ammonium. I have to think here. It's ammonia. Ammonium, I think, is the NH4, right? Or no, NH4 is ammonium. Yeah. So this one here is ammonium. This one here is ammonia. I didn't look it up beforehand. I'm trying to remember my naming rules. So in this case, what is the water going to do? Is it going to donate a proton or accept a proton? Donate. It's going to donate. So if it's donating a proton, which is it? Wait, you said donate? Yeah, it does. Okay. I had to make sure I checked. So that means this is the acid. And what happens with the NH3? Accepts. Ba, bases accept. So we had water was the acid and the ammonia was the base. Yes?
So on the last slide, water was the base. How can it be both a base and an acid?
That was the point of these two slides. That was a subpoint. That water was the base in the first one, now water is an acid. Water can apparently be both an acid and a base. It can either accept a hydrogen or it can donate a hydrogen. It's going to depend on what it's with. And so as we'll see coming up, if you just have pure water by itself, you'll have some that has donated a proton, so with the OHs, and some that's accepted a proton with the H3Os. Question, Jessica.
On this exact one, I'm having a little bit of a hard time seeing like the donates, acid donates.
Okay.
Can you explain that?
Yes. So here we had H2O, right? Two hydrogens. Over here, there's only one hydrogen. So one hydrogen is missing. And notice the charge state, oops, didn't mean to double tick, didn't mean to double tap. The charge state, this now has a charge of -1. If it has a minus sign, that means it has one more electron than protons. So we gave up the hydrogen, but we kept its electron. So that's why we say proton, because we kept the electron, only gave away the proton. So that water is one less hydrogen, but with the same total number of electrons. That's how we define it then, as that's the acid, using this definition of acid base that we're using, which I believe is the only one that we're going to use. We're not going to get too complicated with it.
And we're saying that the base success because it gains.
Right, because it went from 3 to 4. But the number of electrons stayed the same. When it added the hydrogen, it did not add an electron with it. So in effect, we had one proton that went from here to there.
Okay.
Okay, now both of these, notice the arrows were pointing. Pay attention to the arrows per se. I just said we go from here to here. But in chemistry, reactions can go both directions. The reactions don't have to go only one way. So here's an example. What's different between these two slides? The arrow. That's the only difference. And so in this case, we're going to look at the right-hand side and say, which one's the acid and which one's the base? So at this point, who can tell me, is OH here an acid or a base? Okay, you have a base. Why is it a base? It's going to accept a proton if you go from here to there, because its charge becomes more positive by 1, and its number of H's increases by 1. So bases accept means that this is the base. And what's happening with the ammonium? I hope I have ammonium and ammonia right. I'm going to check after class, and I'll just correct myself next class period if I was wrong, and I'll gloat if I was right. Okay, what's it going to do? It donates a proton. So acids donate. directions. That's the acid. Now, if we compare with our previous slide, we had, if it went the other direction, the water was the acid and the NH3 was the base, or putting it together. In a real case, reactions run both directions until you reach equilibrium, so it'll go more one direction than the other, more the other direction. Right, and so you have reactions like this. And so on the left-hand side, the water is an acid. On the right-hand side, the OH minus is a base, because the reaction can go both directions. So this is the most realistic view of the acid-base interaction. Does this acid-base thing make sense on what happens? We haven't talked about why, but make sense on what happens. Okay, I have at least 4 head nods. That's a majority. So here's a question for you to make sure that we have the what happens part. When water behaves as an acid, what does it lose? Yeah. Okay, we have an answer of A, hydrogen ion. Anyone care to agree or disagree with Amber? Lindsay agrees. Anyone else? Grace gives a thumbs up. I assume that's an agree as well. We got 3 people that all agree, and that's correct. Hydrogen ion. What's the word we've been using for hydrogen ion? Proton. Right? They mean exactly the same thing. They're different ways of describing the same thing. So it's not a hydrogen atom. Why is atom an incorrect answer? What's being transferred? Yes, the atom would have to have the proton with the electron. And so it's not the atom because no electron is transferred here. An electron, well, if no electron is transferred, then clearly it's not an electron that was transferred. I think we can agree there. And then there's water can't behave as an acid. Oh, yes, water can behave as an acid. What about a base? It can be a base too. Now, salts is actually an important term. When you say salt, you generally mean the stuff you put on your food, which historically means sodium chloride. But your salt is not purely sodium chloride. You buy your salt and you can find like iodized salt. You guys seen iodized salt? Ever notice that terminology?
That's most salt.
I think so, yeah. Iodized salt has a couple things going for it, one of which is not helping you with taste as much. This one here, you can see it says iodized salt and potassium chloride. Salt supplies iodine, a necessary nutrient. Well, that's one of the positive things. So iodized salt and potassium chloride, those are also salts. Potassium chloride is a salt. And sodium iodide is a salt. So salts aren't just sodium chloride. They are the result of mixing an acid and a base. So if you mix, for instance, an aqueous solution of HCl, hydrochloric acid, and I was going to put sulfuric acid, but I don't want, and sodium hydroxide, I'm once again thinking about the ammonium, if I got that right with hydroxide. Isn't H3O hydronium? That's what I'm using for my identification for ammonium. Anyway, if you mix these two in water, if they're, you mix these in water, so we'll put a parenthesis AQ, meaning that they're aqueous solutions. That's something we're going to have in our homework. It'll say something AQ, meaning it's diluted in water. Then this is sodium hydroxide, which is a base. What will a base do? The base accepts a proton. So what's going to happen is we put that in the water. The hydrogen chloride, it's an acid. It's going to give up the H. So we're going to have H that was given up plus Cl minus when we have the hydrogen chloride in water. And then we're going to have the sodium plus OH minus. And then we're going to have plus water. That's the first thing when they dissolve in water. But now we have these ions floating around. And so we can form a quick ionic bond between those two things. And what do I have when those form? Well, NaCl. And then what will I get if I take these two things and put them together? It's what? Yeah. I'm going to erase that plus water because it confuses your math. So if we mix hydrochloric acid and sodium hydroxide in aqueous form, we are going to produce more water and form this ionic compound of sodium plus ions and chlorine minus ions held together by the ionic force, ion if you wanted to call it that, which we never did. And this here is by definition called a salt. So anytime you mix an acid and a base, if you get a precipitate, that precipitate is called a salt. So you can mix different acids and different bases and get different salts. So now you know when it says salt, it doesn't just mean sodium chloride. So I worked with sodium nitrate as part of my PhD research. That's also a salt. So here are some examples of acid-base reactions producing salts. So hydrogen cyanide, yay, cyanide, and sodium hydroxide. You mix those together and you get water and sodium cyanide. So sodium cyanide, the ionic compound you get when you mix an acid and base, is a salt. Jessica.
Is the salt the only one that can be that an ionic base and an acid?
Well, the definition of a salt is the precipitate you get, or the compound it says here, the ionic compound, formed from a reaction with the acid and the base. So when you mix an acid and a base, the ionic compound you get is called a salt. So anytime you do it, whatever you get, if it's an ionic compound formed from acid and base, it's a salt. Not table salt, right? You probably don't want to put sodium cyanide on your potatoes in the morning. So just some different examples here of salts. Notice this one here. What's different about this one compared to the others? You have two. Now this is what we call stoichiometry. It's not a point for this chapter. It will be a point coming up, and we'll have to do examples. But when you have chemical reactions, you need to have the same number of the same type of atom on each side of the reaction equation. You can't have, for instance, 3 hydrogens on the left-hand side and 4 hydrogens on the right-hand side. In the terminology of chemistry, that's an unbalanced equation. You need to have the same number of hydrogens on both sides. So if you look at this, if it was written without that too, if you had HCl plus CaCl, or Ca, let's see, OH2, read that as a C because that's really quickly, then you would have a total of, well, if there was no 2 here, how many hydrogens would I have on the left-hand side of the equation? Well, the left-hand side of the equation is inside the box. How many hydrogens are inside this box? 3. 3 because the subscript 2 means I have 2 of that thing in parentheses. So this is 2 hydrogens, 2 oxygens. This is 1 hydrogen, so I would have 3 hydrogens. If I look over here, if there wasn't the 2, I'd have H2O and I'd have only 2 hydrogens. With this 2, I have 4 hydrogens. But I need to have the same number of hydrogens on both sides. So with the 2, I have 2 hydrogens plus 2 hydrogens is 4 hydrogens. Counting the rest, 2 chlorines, 2 chlorines. 1 calcium, 1 calcium. 2 oxygens, 2 oxygens. And so we call that a balanced equation. So this is the first time we've seen that necessity. Like I said, it's going to be something coming up, something you're going to have to be doing, I believe, on the homework assignment that's due on Wednesday. This one here, I think is just there because it's a common product that is somewhat confusing. You go to the store and you get pseudoephedrine. What do you get pseudoephedrine for? For your cold. Oftentimes you get pseudoephedrine HCl. That HCl is because you have the pseudoephedrine mixed with hydrogen chloride. Hydrogen chloride, hydrochloric acid, with pseudoephedrine as a base. What you get is a salt, which means that this chlorine here is ionically bonded to this positive ion here, and that's what the pseudoephedrine HCl is. It's a salt of pseudoephedrine and hydrochloric acid. You can also get pseudoephedrine sulfate. The difference in pseudoephedrine HCl and pseudoephedrine sulfate is instead of using hydrochloric acid, they use sulfuric acid. In both cases, you're going to have, in your body, it's going to be processed, and you're going to have that pseudoephedrine that's absorbed. You can't, it used to be this stuff you could just go to the drugstore and you could buy as much as you wanted of it. Now it's regulated. You know why? No. Well, they got that TV series I've never watched, Breaking Bad, about some chemistry teacher who decides to use his knowledge and skills, instead of educating young minds, he decides to use them to make money.
He needed the money.
Okay, see, I never watched it, so I don't know.
He's dying of cancer, his family can't afford it because he's a teacher, so he has to make money. So he sells drugs. You gotta do what you gotta do.
So everybody here but Hosanna should take this as a cautionary tale. You go into teaching because you love to educate and to help people learn, not to make money.
Well, he didn't expect to get cancer and be dying.
True. That was probably part of learning chemistry. You know.
He wanted to just let it happen, but his wife was like, "No, you have to survive. You have a child." Anyway,
the point of my story was not to learn. I now know infinitely more than I knew before about Breaking Bad. Is that pseudoephedrine is something that is very simple to cook into an amphetamine that you can then sell and make money, like in Breaking Bad. And so, because it was so easy to convert it, the government has restricted its availability. So you can't just go buy huge amounts of pseudoephedrine and then go cook it for much more. Yeah.
It's not about Breaking Bad. But there was this mom
That's good.
in Florida that would send like her 2 children in to buy like as much as they could to like every single store like in the area so she could.
That's bad.
Sad.
That's bad. That is very sad. That's, yeah. I'll start ranting if I start talking about that. So we'll just move on. What salt forms with the reaction of HCl plus potassium hydroxide, KOH? Okay, so I have an answer from Amber. What did you say? Okay, so Amber says that's going to form, I read E. I was like, really? So KOH2Cl, she says. Are we agreeing or disagreeing with Amber?
I agree.
We have one agree.
I agree. 2 agree. Just good.
This time around, I'm going to have to disagree.
It's C.
It is. Actually, yeah.
Why does the CL drop off?
It should be, it's A. It's A. I should read these more carefully. What's going to happen is you're once going to have these dissociate. So it dissociates, and then you're going to have this and this form a salt. That's going to be an ionic compound. And we're going to have these form water.
I see. Boy, how do you know which one's going to be on
That's a good question. How do I know which ones go together? The ones that aren't OH and H is my simple answer for you.
So they're always
It's not that simple. But we're going to form water and a salt in our simple reactions that we're going to do for this class. So you look and say, okay, what's going to form water and what's left?
So we're only doing reactions that form salts.
Right now with our definition of a salt, yes.
In the future, we could do other reactions.
Yes, we could. So you understand how that worked? It's a lot easier when I'm describing it than it is for you to sit and look at it, right? It takes a different level of understanding to nod and say, yeah, I can see how that works, and then to look at it and do it yourself. But remember the definition of the salt here, an ionic compound. Nice job. Ionic. Compound formed from the reaction of an acid and a base. In this case here, it didn't form water, did it? In this practical example, the hydrogen went from there to there, and then we had the ionic bond between chlorine and the rest of it. There was no water involved. So it doesn't always involve water, but our simple cases will. First thing I want you to note from this picture, safety. The reason we should have no food or drink in the classroom here is for safety. The same reason that he's wearing his goggles. Right? If you're working with something like, say we're doing something with hydrogen cyanide, you wouldn't want to get any of that in your body. Right? It's just not good for you. He's got his eyeglasses on to keep any splashing of this stuff from getting into his eyes. Getting onto your skin is bad. Getting to your eyes is much, much worse. That's why we have to wear those for last lab period. Because we want to make sure that we are being safe. And that's why we absolutely had no food or drink in here for lab last week. Because we want to make sure that we are safe in what we do. So, this here, the point of this slide is actually simply the word strong. Strong acids and bases ionize completely in water. So that means if I put HCl in water, all of the H's and all of the Cl's separate. So I don't have any HCl's bonded together.
So then ionization is separation?
In this case, yes. Ionization technically is you lose or gain an electron. But the way that's happening here with the acid is you're dissolving and separating the things. So all of the hydrogens separate from all of the chlorines. You don't have any HCl's by themselves, at least if it's a somewhat dilute solution. If you had like 99% HCl and 1% water, that wouldn't be possible. But if it's a reasonably dilute system, if it's a strong acid or base, it completely ionizes. If it's a weaker acid or base, it'll only be partially separated, partially ionized. And notice once again, she's wearing her goggles for safety. I don't know. If I'm working with, she's working with weak, not so much of a concern. If I'm this young man working with something strong, I might wear gloves too. You know, just to be smart. How do we see relative strengths? Well, I don't have this example. I bet you they do up in chemistry. I could have borrowed stuff and done this, but I didn't think about borrowing. You have a light bulb here that's run on a battery. That is what a battery is. A typical battery like you have in your car, you have some lead and some oxidized lead. So 2 pieces of metal, and you put them in an acid. And that acid causes chemical reactions that are different at the 2 things. And the stronger the acid, the stronger the reaction is going to be. And so this one here, this is just plain water. Just plain water. Now, we said water can be an acid or a base. Well, if it can be an acid or a base, it's a really, really weak acid or a really, really weak base. And so you have nothing going on there when you just put them in water. If you put them in a stronger acid, you'll have a bigger reaction. The bigger the reaction here, the brighter the light bulbs will work. So which acid in these pictures would you say is the strongest acid? The middle one, because the light bulb is burning the brightest. And so this is a way that you can determine the relative strength of acids. So one thing that's common, my son did this for high school science, or that was grade school, science project, is to make a battery using something like an orange or potato, something that's acidic. Right? Oranges, you've got that citric acid. It's acidic. You put in a piece of copper and a piece of zinc, basically a nail that's been anodized, and you'll create a voltage because of the chemical reaction with the acid. And the stronger the acid, the better the reaction is, the higher the voltages you're going to produce. Water. I just said water could be both an acid or a base. Remember that was pointed out by Amber when we had those 2 slides there. Wait a minute. It was an acid, now it's a base. What's going on? It can be both. And so here's a reaction showing water reacting with water. Now that's bizarre, right? But you can have this reaction. You have 2 water molecules. One of them gives up a proton. If it gives up a proton, which thing is it? Acid or a base? Okay. Acids donate, so it's an acid. So I have this water molecule here was an acid because it gave up. And then the other one was a base because it accepted. And so here we have the terminology to make it straight. The ion is hydronium, so the NH4 ion would be ammonium. So we have this process. Now notice it shows the reaction going forward and backward, going both directions. And you're going to reach an equilibrium, a balance. So when we take this mixture of water, what we're going to do is measure the concentration of these things. So when we put the chemical formula in these brackets, that means the concentration. Now we had concentration not last week, but our last week of class. What was the unit of concentration that we learned about? We learned the concentration was blank divided by blank, and the unit we used was, okay, first I'll put, it's the solute over the solution. And then we had what units do we measure the solute in and what units do we measure the... Let's even back up one step further. What does solute mean? The minor component. And what is solution? The entire thing. So we had units for it. Do you remember what unit we used? It's not what you have to use.
ppm.
We did talk about parts per million, but the one that I spent the most time on would be before that. We measured the amount of solute in moles.
Oh, yeah.
Where a mole is 6.022 times 10 to the 23rd molecules or atoms, depending on the appropriate case. So the concentration here is going to be measured in... Okay, I'm going to just move this because I can't write right to left and have anybody make sense of this if they look at it later. go away. In moles per, and then we measured the total in units of volume, liters, moles per liter. So that's what we're going to measure. It's called the molarity, by the way, if you want the name for it. That's what we're going to measure our concentration in. And so my bracket OH means the concentration of OH. So how many moles of OH do I have per liter? Now, given this reaction, you're going to have the same amount of OH as you have H3O. So these are going to be the same value. And it turns out that in pure water, you have 10 to the minus 7 moles of OH minus per liter of water. You also have 10 to the minus 7th moles per liter of water of H3O. So that's telling us about the concentration of the OH or the H3O. Now we're going to only focus on one of these. In general chemistry, you also only focus on one of these. You go to higher level classes and they'll start talking about both of them. So, okay, I just talked it out, and now here I have it written, just so you have it there, black and white instead of red or blue. When we talk about how acidic or basic something is, we compare the concentration of OH to the concentration of H3O. If it's the same concentration, we say it's neutral. It's neither acidic nor basic. If it has more H3O and less OH, then it's acidic. If it has more OH and less H3O, it's basic. So remember, basic things, I should stop using the word basic when I'm talking about bases, right? But with your measurement of acidic or basic, since acids donate, if you have more protons, then it's acidic. So if you have more H3O, that's the one that has more protons, it's going to be acidic. So let's go a few slides further. We call this thing pH. Everybody probably has heard of the term pH. Haven't you? Is pH important? Is it important for your body chemistry?
Yes.
Yes. Your body chemistry, your pH of your body is something like 7.34. I might have the number a little bit off. It's almost exactly that. If it differs by more than about 0.04 from that value, you know what happens to your life? It ends. Your body is well buffered. It's going to maintain that acid. No matter what you eat, your body is going to maintain it. It might do things like take calcium from your bones to help buffer and keep your bloodstream so that you can live. Question?
Or is it acidic if it's between 0 and 7?
It is acidic if the number is a lower number than 7. It's basic if it's a higher number than 7. What was that?
It can go in the negative?
It can.
Yeah.
What's the most acidic thing humans know of?
The what?
What's the most acidic thing that's in existence that we know of?
Actually, I have a slide with that. I don't know on the top of my head, but I think it's going to come up in the slide. Because, yeah, it's always a very useful question, like, how acidic can things get? And the question, so it can go positive. So how do we get this value? This is the mathematical equation for calculating the pH. The P, in my mind, it's something to remind me that I'm measuring how much, so I think of percent, but it's clearly not percent. The H is measuring how much excess protons we have. And so pH is telling us how much excess protons we have, and to make it an easy calculation, we use a logarithm. How many people are comfortable with logarithms? Okay, I have a few that are shaky and one that said yes. So what a logarithm means is what exponent would I have to raise my number to, or would I have to raise 10 to get my number? So for instance, if I have log, and technically this is log base 10 of 100, what power would I raise 10 to get 100? Not 10. 10 raised to what power is equal to 100? 10 squared, right? 10 squared is 100. And so this is just 2. Because if I take 10 and raise it to the second power, I have 100. So in the case of neutral water, I have a concentration for hydronium of 10 to the minus 7. So 10 raised to what power is 10 to the minus 7? It's kind of a redundant question, right? 10 raised to the minus 7 is equal to 10 to the minus 7. And so the log of 10 to the minus 7 is just minus 7. We have the minus sign out front in our definition. So the pH of neutral water is 7. So a pH of 7 is neutral, not acidic, not basic. If we have more hydronium, then it's going to be something like 10 to the minus 3. That would be a bigger concentration. And so you have log of 10 to the minus 3 is minus 3. Minus a minus 3 is plus 3. So a pH of 3 is more acidic. And what if I had a concentration that was like, well, that was, let's say, 10 to the 2 moles per liter? That's certainly possible. If it's 10 to the 2, what's the log of 10 raised to the 2? 2. And then I have the minus out front, so I could have a negative pH there. That's just a stronger acid.
So technically, if the number isn't negative, like next to the 10, it'll probably always be acidic.
Oh, definitely. Not just probably. Yes. Right. It's super acidic, super strong. So, yeah, I don't know why I have that again. So here's just some examples. And notice our textbook goes from 0 to 14 on the number scale. I mean, when I was in high school, we basically learned that pH goes from 0 to 14. But it's not true. What would it mean if I had, well, we've already talked about, if I have a pH that's negative, right? That's off the bottom of the scale. It's super, super acidic. If I have a pH that's bigger than 14, like a pH of 17, what does that mean?
Does that happen a lot?
I don't know that it happens a lot. But it would be super basic.
But it does happen.
I believe so. I wish I had encyclopedic knowledge to simply say yes or no. Okay, as sodium hydroxide, NaOH, is added to water, the hydroxide ion OH concentration, how does it change? If I put NaOH in and the NaOH separate, what's going to happen to the concentration of OH?
Decreases.
It's going to increase because I'm adding those OHs. Right? Because initially I had the water was 10 to the minus 7 for the concentration. I add sodium hydroxide, the OH separates, and now I have an additional OH for each sodium hydroxide I add. So the OH goes up. But remember the balance that was shown in these previous pictures. If the concentration of OH goes up, what happened to the concentration of H3O? It went down, and so that's making it more acidic. Now, sodium hydroxide is a base. Yeah, it's a base. Wait a minute. It is a base. The concentration of sodium hydroxide goes up, which means the concentration of H3O goes down, and goes down is going to make it go. I actually wrote this wrong. I was like, wait a minute, something's wrong here. This is showing as a teeter-totter, so it's more amount, so it's shown down, and it becomes a base. Wow. Great way to end the class period. Let me find the graph that shows some substances. So here you have concentrated HCl has a pH of -1, an example of a negative pH. And it doesn't show anything that's more basic than 14 for the pH. And so you have, blood is just slightly acidic here, like we said. And we'll stop there. Have a great Monday as you get back acclimated to school.